Last time. He has plenty of other homework. Don't worry. No, I need him to be doing. Yeah, he's busy. Don't worry. Last time we solved this Diophantine equation. Not just Diophantine, Diophantus's, literally Diophantus's equation, whatever it was, x squared plus x to the 4 plus x to the 8 is y squared. It's actually a very interesting curve. It's a higher genus. I mean, one of the only ones that he. Anyway, we found a rational point. The point was to solve this thing over Q, and we did so via the introduction of p-adic numbers via
What
Q.
year was this again?
This is like 300 AD.
He was asking for solutions.
Yeah, he was posing these problems and solving them.
Now, when in the Middle Ages did people start looking at this stuff again?
Oh, well, this stuff got translated into Arabic first and foremost. So he's in Alexandria. The Library of Alexandria is burned first by Christians. This is a long story here. Around in the 300s, the Holy Roman Empire becomes holy. The Roman Empire becomes the Holy Roman Empire, right? Constantine converts, and then by 100 years later, the entire Roman Empire is supposed to be Christian.
Right.
Then the Arab armies. So the Muhammad. Let's not get into world history. The Arab armies conquer North Africa, including Alexandria, burn down the library, but also a bunch of people come around and see what else, what they can salvage, and they bring it to Baghdad. And Baghdad is the cultural capital of the universe for the next, nearly 1,000 years. So it's in Baghdad that the Hindu numerals, which maybe came from China to India, made their way to Baghdad. And then Fibonacci, during the Crusades, another happy time in the world history, Fibonacci comes down and learns the Hindu Arabic numerals, brings them back to the West, and that's the 1200s, and now we're off on the Renaissance in Europe. So anyway, that has nothing to do with p-adic numbers, but so Diophantus solved. So we solved this equation. So what are the p-adic numbers? The numbers that look like a n p to the, maybe I should call this a minus n, p to the minus n plus a to the minus n plus 1, p to the minus n plus 1, down to a negative 1 p minus 1 plus a 0 p to the 0 plus a negative 1 plus a 1 p to the 1 and a 2 p squared, and so on. So the only difference between real numbers and p-adic numbers is there's infinitely, it looks like it's getting infinitely large. There's infinitely many terms this way as opposed to that way, which is the opposite of how real numbers go. All right, we talked about how these are the completion. This is completion, metric completion. Actually, that's a fun conversation. Yeah, maybe I'll tell you about that. Metric completion of Q with respect to the norm, in other words, a distance function induced by the p-adic absolute value. This is the p-adic absolute value, which for a natural number, if n is a natural number, then its p-adic absolute value is, yes, exactly, 1 over p. Let me write it like that. EPN is the number of times the prime p divides n. So number of times p divides n, the multiplicity with which p divides n. This is equivalent. There's no reason to put a 1 over there. There is reason to put 1 over p there, but this is equivalent to lambda to the EP for any lambda less than 1. This was a normalization, yes. And we proved Ostrowski's theorem. That any non-trivial, well, that the only, only non-trivial completions, only non-trivial metric completions of Q are QP and R.
When was this proven?
1920s, I want to say, but don't quote me on that. homework? Somebody tell me what year this was.
And it should have been because like, that's when these objects started becoming popular, or was it?
That's a really good question. For the purposes of what we're doing, automorphic representations, Tate's thesis is sort of, for me, the birthplace of when these things become, you know, the essential tool of anyone working in this field. That's 1950.
1916.
1916. I wasn't far off. Very good. Thank you. Okay, 1916. So these things were around. People were thinking about them. They were. I mean, Hensel is 18. Hensel's lemma is late 1800s, right? Yeah, I should mention the way that we solved this thing, what we got here was through Hensel lifting.
And that was for the solution of the.
Yes, this, which is not how Diophantus solved things. Right.
Because the Hensel's lifting was just like a theorem with like.
Yes, I didn't state the
Right.
you want the you know non-vanishing gradient of your, if you have a solution, then the condition that allows you to lift it.
Right, but presumably Diophantus was doing this sort of intuitively.
He had a variety of rather remarkable techniques for solving polynomial equations in rationals. This is why Fermat was reading Diophantus' Arithmetica. That margin, that's the book. That's where that margin is. It's Diophantus' Arithmetica where he puts the last theorem. All right. Yeah, I wanted to say, in some sense, I mean, I don't know if this is really historically accurate, but at least pedagogically, one way to introduce the p-adic numbers is what we did last time through this Hensel lifting. And in that sense, the p-adics kind of play a similar role to solving rational equations as complex numbers to solving the cubic equation. People were trying to solve a cubic equation. They didn't care about complex numbers. They had to invent complex numbers in order to get to the real root.
Right.
And much later, complex numbers become a thing in and of themselves.
You're saying a similar thing in that.
The way we're following it is in a similar way. I don't know if that's historically accurate. It seems to me it is, because that's kind of what Hensel was doing. We found a rational, all we wanted is a rational solution. We had to invent these other numbers through which to find a rational solution. But now we're going to start studying these numbers in and of themselves.
These geometric series.
Exactly. Making sense of this geometry, putting a metric on which we can actually work with these honestly and not hand-wavy. Okay. This completion stuff is kind of, okay, this is a total aside. This is not what I want to talk about. But here's the funny thing. The real numbers are they are metrically complete, of course. Cauchy sequences of real numbers converge to real numbers, but they're also almost algebraically complete. Which means, so what is R bar? The algebraic closure of R. Well, what do I mean by, what's an algebraic number? So let's say F algebraic number over a field F or ring, whatever. F is let's say a field or a ring, whatever structure you want. It's kind of equivalent because, well, anyway, what's an algebraic number? So let's say alpha is F algebraic if, yes, exactly. We want to solve, algebra is about polynomials, right? Polynomial equations. If there exists a polynomial with coefficients in F, such that this polynomial, so that alpha is a root, that alpha vanishes. Okay, so the algebraic closure is you take all solutions to polynomial equations with real coefficients. And what is this? Everyone knows. Yeah, there's only one. All you need is to take a single polynomial equation, x squared plus 1, that you can't solve in the reals, adjoin that one root, and you have the fundamental theorem of algebra. Now any polynomial is solvable. So then we have fundamental theorem of algebra. R bar, better known as C, is algebraically complete, i.e. any polynomial i.e. any polynomial with coefficients in C has solutions in C. Right. We need a single degree 2 extension of the reals to get something that is algebraically complete and it's metrically complete also. And C is metrically complete. C is metrically complete. You don't notice that this is like some magical miracle until you see what can happen. Metrically complete. Right? So for I'm not going to prove these things because I don't need them, but just FYI, for fact, this is the fact, unproven fact. So you take QP, you take polynomials in QP, and you solve all of them. So here's an exercise for which P is the same polynomial x squared plus 1 solvable in QP. Okay, try to solve. So for some P's, you will be able to solve this polynomial. For some P's, you won't. Some of you already know the answer. If you don't know the answer, it's a very fun exercise. If you really want to get, understand these things. Okay, so for those P for which this isn't solvable, fine, we adjoin that root. It turns out we need to adjoin infinitely many polynomials. This is an infinite extension. Unlike C, which is a quadratic extension of R, this is an infinite extension of QP. You can extend this p-adic metric, this norm extends, and QP bar is not metrically complete. So now you go, oh crap. So we're going to start with Q. We're going to complete it, so metric completion up to QP. Then we're going to algebraically complete up to QP bar. And who the hell knows if this thing just doesn't go on forever? There's no reason for this to stop. It's an absolute miracle that it stops when we do it in the reals. We metrically complete to the reals. Then we take this quadratic extension to the complexes, and then we're done. It's algebraically closed. It's metrically closed. We can take Cauchy sequences. We can solve polynomial equations. There's no reason for this not to stop. Anybody knows how much farther we have to go? Yeah, that's the last step. So CP. So CP, if we metrically complete the algebraic closure of the p-adics, now it's metrically and algebraically.
So Joey and I were actually months ago. I'm pretty sure. I'm sure I'll believe you once you ask your question. If you go Q to Q bar and then metrically, you end up at CP or something else.
You do well. It becomes subtle. It becomes subtle. If you go from Q to Q bar first, if you algebraically complete first,
then you can go to C.
Yes, you can go to C. You can go to C by taking Cauchy sequences in Q bar with so this metric completion with the infinity absolute value is fine. It gets delicate to do this part. The extension is not, there's not a canonical, there's not a unique extension. But if you fix an extension, then the whole process continues in the same way.
We get stuck on how you find that.
Okay, yeah. The question is, what norm do you want to, what p-adic norm do you want to put on Q bar? And how are you going to sort of continue this story? But yeah, that's a fun aside.
But okay, so let's say I already know about how to get the CP going right.
Yes.
Then that gives me a norm on Q bar, which I can just take out of the back of my head and put on Q bar.
Yes, yeah.
So then if do I get CP?
So C and CP are isomorphic as fields.
True.
These two guys. But of course, their structures are completely different. So you can take if you take CP and you pull that norm back to Q bar and then start doing the completions, you will get back the same CP.
But is it just one step?
That's
what we really want to do.
If you first algebraically close, and then you complete with respect to that norm, I have to think about this. I have to think about this. Okay, so the question is, when you're doing this closure, right? I have to think about this. Because when you let's say you close this up. Let's say so there is a non-canonical way to do this extension, and when you do, you get I don't know. I'm running out of ways to call things. There's the bars and a P and So if you close algebraically and then you close metrically, now you want to see if that's algebraically closed with those coefficients. That's a pretty funny thing. It might be that it jumps straight to CP. I don't remember.
Okay.
I don't remember.
I think if you close algebraically, you get non-canonical isomorphism between two triple bar and C. So this one, because I wanted to see just regular C.
Yes.
non-canonical.
Yes. Yeah. Anyway, this is not what I want to talk about. But it's good to know and fun to play with. All right. So what we want to build up to is we want to do calculus on QP, right? We know how to do calculus on the reals. We have Lebesgue measures and all this good stuff. We want to build up to calculus on QP. The first thing, if you want to do calculus, then what's a continuous function? What's a topology? So let's try to understand the topology. Let's work our way towards, we want to make progress on understanding the topology on QP. Of course, we have a norm. We have this distance function, which we got from the absolute value function. So we want to try to understand what the induced topology from this norm is, from this metric. So we have a metric. So this is now a metric space, and let's understand this metric topology. Okay, here's an exercise. I hope you guys have pen and paper. Sometimes it's good to work something, if you start falling asleep, then here's an exercise. All right, give me 3 rational numbers.
0.
Other than 0. Come on, with fractions.
17 over 5.
17 over 5. Another one.
Floor pi over floor.
Floor of pi over floor E. Yes.
I'll give you 15 over 9.
Beautiful. 15 over 9.
Sorry. 35 over 9.
35 over 9, even better. And then in Q5. Okay. So here's a triangle. Here are 3 points. What are the distances? So I want to know A minus B in Q5, A minus C in Q5, and B minus C in Q5. Okay, take 1 minute and work this out. They're all going to be 1, aren't they? This is going to be boring. No, but I'm subtracting B. Let me do 20, 3 over 20. There we go. Okay, now it's going to be slightly non-trivial. Okay, so A minus B. Got it. We really have to do this, don't we? There is a purpose to this. Okay, 17 over 5 minus 3 over 20. I can pull out a 1/5, and then I have 17 minus 3 over 4. 17 minus 3/4 is going to be 17 is how many quarters? Whatever it is, it's not going to be divisible by 5.
Are you sure on that?
I'm hopeful.
17 times 4 is 68, and 68 times 2 is
68 minus 3. Oh my God. Over 4. All right. So this is 65. 65 only has 1 5 in it. So this 5-adic norm is 1. All right. A minus C. This is what I get for not preparing these in advance. 35 over 9. But I don't like, you cook something up and then you don't get to feel what it's really like. 17. Yeah, there's no really good way to do this. Okay, 170 minus 17 is 153 45ths. And 35 times 5 is 150, and 25, 175. And I want the 5-adic norm. You can no, this definitely is not divisible by 5. This is, so this distance is 1/5 in the bottom here, so it's 5. Everybody got that, I hope. So that was A minus B, A minus C, and now B minus C. Let me put it here. I think I have room. B is 3/20ths minus C is 35/9, and the 5-adic norm of that. Okay, nothing in common. I have 18. Sorry. Yeah, thanks. Now that's really embarrassing. 700 and 20 times 9, whatever that is, I don't need to know. This is not going to be divisible by 5. The bottom is, so this is 5. We took a totally random triangle. You provided these things. I did not cook them up in advance. And we got an isosceles triangle. That's fine. Okay, fine. Everybody knows. So theorem, lemma, whatever. Lemma. Every triangle in QP is at least isosceles, maybe equilateral, probably not. Okay, why is this true? What made these things come out to something? That's right, the super triangle inequality. Okay, the reason this is true. Okay, maybe you guys all know this. You know what? Some of you know this, and some of you know this very well, but I did not assume that you. That's those of you that have familiarity with the p-adic numbers, and many people don't. So we're going from the ground up. We're going to take it nice and easy. Right. So why is this true? It's true because of the super triangle inequality. Inequality or an ultrametric inequality. Well, okay. It sounds made up. You mean the technical term?
Yeah.
I don't think that's it. Is it the super triangle inequality? There's definitely ultrametric is definitely a term. So ultrametric property. Ultrametric, you know, if you have the distance from X to Y should be no more than the distance from X to Z plus the distance from Z to Y, right? That's the triangle inequality in another form. And the ultrametric property is not just the triangle inequality, but actually it's the max of the distance from X to Z to the distance from Z to Y. So to get from X to Y, the distance from X to Y is no larger than going from X to Z plus going from Z to Y. That's the standard triangle inequality. And the ultrametric triangle equality is that to get from X to Y, you can just go to, you know, it costs nothing to go to, it's the same as either going to Z or going from Z to Y. That's the same thing as every triangle is isosceles. One of these is already either X to Z or Z to Y is already long enough to be an upper bound for the distance from X to Y. Okay, and again, so why is this? So this is the metric version, the triangle inequality, the value, absolute value version is that X plus Y in p-adic norm is not only bounded by the sum of the X norm and the Y norm and the Y norm, but actually it's bounded by the max, which is the same thing when you take Y equals 0 or Z, whatever. This distance is the distance from X plus Y is the distance from X plus Y to 0. And this is X to 0 and Y to 0. Same thing. Why is this true? Exactly. So if X is so proof or sketch, whatever. Sketch, if X is you know, a to the minus n, p to the minus n, and so on, and Y is a to the minus L m, p to the minus m, and so on. So when I add X and Y, if m and n are different, then let's say n is greater, let's say n is greater than m, then whatever gets added is added in lower digits and does not affect the so the absolute value of X, if I'm assuming this leading coefficient is not 0. So the leading coefficient is non-zero, then when you add Y, you only change these lower digits. And so that doesn't change the absolute value of X is not changed by adding Y to it. And so X is already big enough to be an upper bound. The norm of X is already big enough to be an upper bound for the norm of X plus Y. Does that make sense? So, and that's exactly what's going on here. Okay, so that's the ultrametric property. The ultrametric property tells us something very fascinating. Let's look at, so how do we get a topology from a metric? Exactly, right? So what are the open balls? Open balls in QP, we're not in kindergarten, right? What's a ball around a point X in QP of radius R? R is now a positive real number, right? We have to keep track of what variables are in this weird QP and what variables are real. What does this mean? It's just exactly what it's supposed to mean. It's a set of y in QP so that the distance from x to y is at most r. Right? These, if anything is going to be called open, these are the things we should call open. So these balls we will call open, and the topology on QP is induced by these balls as a basis. In other words, you declare any such ball to be open, arbitrary unions, what's the topology? Arbitrary unions of open sets are supposed to be open, finite intersections of these things are supposed to be open. Okay. Well, what is one of these balls? Okay, so what's the, here's another exercise. What is the ball in 2 times 5 to the minus 2, I was right the first time, plus 1 times 5 to the minus 1, plus 3 times 5 to the 0, plus 2 times 5 to the 1, plus 3 times 5 to the 2, and so on, of radius a half. Describe for me, please. Let's make it a little bit more interesting. Radius a tenth. What is the radius 1/10 ball around this point in Q5? Yeah, give me a, so which y's, what does y in QP have to look like so that its distance to this point is less than a tenth? Oh, you're telling me what it is. Yes, okay. So how many first terms are the same? You say the first 2 terms have to be the same. Why do you say the first 2 terms have to be the same?
Well, because it could be one term with the first one fixed, but
if this coefficient of y differed, it wasn't 1, then when I take this point x minus y, so let's put it this way, the distance from our x, let's call this x naught, to the point 2 times 5 to the minus 2 plus 2 times 5 to the minus 1 plus whatever else is, so when I take the difference, this leading coefficient 2 times 5 to the minus 2 cancels off, but now I have something with a 5 inverse. So this distance actually is 5. The distance between these two guys is 5. Okay, so I'd better get this coefficient right. I had better get the next one right, because if these two differ, now I have the distance between them would be 1. I had better get this one right, because if these two differ, then their distance is 1/5. Now, if they differ, the distance is 1/25. Okay, so this can be whatever it wants to be, a2 a to the squared plus a3 5 cubed, and so on, and these are free. These variables are free. These variables are fixed, required, restricted. Okay. Does that make sense?
One thing I want to mention, when we define QP, you should have mentioned that all the coefficients are from 0 to p-.
Yes, I think I did. Maybe I didn't say it. Yeah, last lecture. Yes, all of the AJs are in 0 to p-1. Just like a p, decimal expansion in base p, except obviously going in the other direction.
Very nice.
It wouldn't be a very nice expansion if it wasn't this way. Yes, exactly. All the coefficients range from 0 to p-1. Yeah, thanks. Okay. Do you guys know about I'm not assuming ergodic theory. You don't need to know any ergodic theory. If I have infinite coin flips, heads, tails, right? So I have 0, 1. So this is an aside. We've answered the question, right? This is what a ball looks like. If I have 0, 1 to the n, so I'm thinking of, sequences like heads, tails, heads, tails, whatever, right? Infinite sequences of heads and tails, and the collection of all such things. What are the cylinder sets in this infinite product? Anyone What's that?
They might want to specify the cylinder.
I'm asking, do you know what cylinder sets mean? Okay, a cylinder set means it's a set where you specify the first bunch of digits and then the rest are free. So this is a standard construction in all kinds of subjects, including ergodic field. So this is exactly a cylinder set. A ball, a p-adic ball, a QP ball is a cylinder set where the first digits are specified, are restricted by the center, and the rest of them are all free. So in QP, the balls are these cylinder sets. Every open ball is a cylinder. This is exactly. This is exactly what goes on two-adically, but it's no different. I mean, instead of 0, 1, we have 0 to p-1 to the end.
Right.
Well, this is actually ZP. Okay, we're going to get to ZP in a second because we can go, a couple steps in that direction. There's a little bit more information in QP. There's no addition. Yeah. This is not a. In Z2 we carry ones. Yes. All right. So the balls are cylinder sets, and this has a funny consequence. If Y is in a ball of radius X about R, then the radius R ball around Y. Okay, those of you that know this stuff, let the other people enjoy getting their minds blown by this crazy topology. What this means is if you have a ball, I have a ball around X of radius R, and I have some other point Y in there, that point Y is also a center for that ball. X is not a unique center. Any other point doesn't have to be X at all. And that point is also a radius R ball around Y.
There's so many geometry things about this that are like so non-intuitive.
Yes. It sounds fake. Yeah. Then this ball is the same ball. Okay. So any point, i.e., any interior point of a ball, interior point of a ball is a center. That's the right reaction. Thank you. Thank you. Someone is appreciating this. Any interior point of a ball is a center. So centers are far from unique. Okay. All right. What other crazy things that I want to tell you about? Is it Hausdorff? Great question. Okay, let's start asking some good questions. Is QP Hausdorff? So what does Hausdorff mean? Does everybody know? Let's remind. There's like T1 space, T2 space, T3 space. Hausdorff is T2. Yes. So what is this is called T2. Yeah, separable by open sets, right? If I have, so is it true that for all X and Y in QP, there exists open UV open such that U and V are disjoint, and X is in U and Y is in V. So if I have 2 points, can I separate them by open sets? Not just separate them. There's an open set containing one but not the other. There's like all kinds of complicated. This is the T2. Okay, Hausdorff. Hausdorff is the best notion. We don't need the other. Is it true? We have a topology. Is it true that we can separate sets, points, by open sets?
I think the question is, you have to find a different radius. So you have two things that are in some small, you have to find smaller radius.
Yes, how? Okay, so let me give you 2 points. 2 to the 5.
R is density, Q and Q is density. So we would do something
We do not want to use R.
okay, well, I just don't know if we can get them so close. You could choose 2 of them that are so close that there's no radius small enough.
So, by the way, they have to be, of course, be different.
Yeah.
So if they differ,
The question reduces to whether you can find a radius small enough. To have this.
okay, well, good question. What's that?
Please find the
Place where they differ.
Yes, you find the place where they differ.
The first place. Smallest place.
So here's the smallest place where they differ. Now what?
Choose a radius of 1 over that.
Yeah, we can make these all free. And that's a cylinder set. We can make these all free. And that's a cylinder set. So that's an open set containing X. This is an open set containing Y. So we free these up, that makes a U. We free these up, that makes a V. U and V are disjoint because they differ. Any point in U differs from a point in V because they all differ at this digit. This way is, thanks. I'll keep doing that, so please keep. Yep,
So it is.
so it is house tour.
Isn't it true that every metric space is
Yeah, that's.
But here we want to actually feel it. Yeah, so what's the, here's another question, is QP compact? Thank you for, yes. Not ruining it. Compact in the standard meaning of compact, we have open, for every open cover, can we find a finite subcover? You say no. Don't tell me. No, tell me. Did you tell me your name? Tell me your name. Jish. Yes. And did you want to do homework? Probably not. Fine. Jishen, go on. Why do you say no?
Because so what I should do is find the open cover and prove that you cannot find a finite subcover.
Beautiful. That would certainly prove non-compactness.
No, I think you just pick up every point and look at the ball. These are every point with previous given number, and then probably you cannot find a finite subcover.
That's exactly what you can do, and you can take that point to be the origin. So let's say we take here's a bunch of covers. Here's a bunch of open sets. O0 is a set of all A0 p to the 0 plus A1 p to the 1 and so on, right? That's obviously a cylinder set. These digits are all free. O1, maybe I should call this O negative 1, but okay, you'll keep me honest. This is p to the negative 1 plus O0. And O2 is A minus 2 p to the minus 2 plus O1. Okay, and QP, and any element in QP is going to lie in one of these. So QP is contained in the union of these OJs. That's an open cover.
Yeah.
Why? Why can't I find a finite subcover? They're all contained in one another. I have containment. OJ is contained in OJ plus 1, right? This is contained in this one.
Yeah, like it doesn't.
Even if it wasn't, it doesn't, yeah, exactly. It doesn't stop. So the point is, if there was a finite subcover, if there were,
Seems very similar to real construction.
if there was, or if there were to be, if there was, I think it's were.
Where is fine. Where is
Yeah.
fine.
We'll get an English major in here. If there were a finite subcover, right? Whatever the largest n is, that's it. The cover finite subcover would be a singleton. It would be a singleton. It would be a single ON, and of course, that's not going to cover QP. Okay, so no. So the answer is no, not compact. How about Z? Okay, so what is this thing called? I give it away. This thing is called ZP. Why is it called ZP? What are the integers? Let's in R, the integers. Can't see the clock. It's hidden behind. Okay, we're doing good. The integers are, what is the integers? It's all these decimals, right? N 10 to the n plus a n minus 1 10 to the n minus 1 minus. I know you're watching. Plus a 0 10 to the 0 plus a negative 1 10 to the -1, and so on, except all of these guys are 0. Right? So there's nothing after the decimal point. That's what the integers are. Nothing after the decimal point. Nothing after the decimal point. Okay? In QP, ZP is the set of all things that look like AN p to the -n. I guess I'll call this A minus n p to the -n, A minus n plus 1 p to the -n plus 1 down to A -1 p to the -1 plus A0 p to the 0 plus A1 p to the 1. This is the direction in which I can go on forever. But these guys are all 0. This is the decimal point.
If we keep getting rid of finite stuff in one case.
That's right. That's right. I only want this finite, yeah, because they go in different directions. So this is what's called ZP. Is this even a ring? If I add, subtract, multiply things in ZP, do I stay in ZP? Can we characterize ZP in another way? So is ZP a ring? Why? Yeah, you can sort of see it just on the level of what that multiplication will do. It'll never introduce, if you might multiply two things like this, it'll never introduce negative powers of p into the expansion. That's certainly so. Yes, you can see it from that point of view. Is there another reason, Philip?
It's also an inverse. Right.
It's also an inverse limit. We'll get to that in just a second. I do want to discuss that because that's actually what we did when we solved diaphantus. Yeah, let me come back to that. What's that? The inverse limit is apparent from what's written down, but I want to spell it out. Yes, it's apparent for those in the know. I'm not assuming anyone. Yes, I'm not assuming any background. Can we describe ZP as a ball? Well, is 0 in ZP? It's a ball. Yes, if it's an open ball, I can't quite say radius 1 because open means radius strictly less than 1. So it's a closed, so I can say 1 plus epsilon. So the distance to 0 is allowed to be 1. Right? The number 1 is a distance 1 from 0. So it is a ball. If you like, it's a closed, can I write this? Closed ball of radius 1. So it's all the things, a distance 1, distance at most less than or equal to 1 from the origin. In other words, it's the set of all things in QP whose p-adic norm is less than or equal to 1. That's the next question. Is ZP compact? Should I do that first, or let's talk about the inverse limit? Just to, I owe you two things: inverse limit and compactness. So ZP, okay, as you guys already said, is the inverse limit of these quotients z mod p to the n z. What does this mean for so those that haven't seen these kinds of things before? We z mod 5 squared has a map onto z mod 5. That map is called mod 5. Right? If I know what the number is mod 25, I also know what it is mod 5, just by reduction mod 5. I also have a map, I also have z mod 125, which I could reduce mod 25. Well, I could also reduce it mod 5.
What kind of structure do you use maps?
So as long as I have, there's an abstract nonsense way to define inverse limits, which is if I have a bunch of sets and I have maps from larger index sets to smaller index sets that are compatible. If I do one and then the other, it's the same as going all the way down. Then I can take the inverse limit of that collection of sets. And that's an abstract definition. Was that? Sometimes. I have to be a little bit more careful than what I'm saying. Okay, so this is clear, right? Z mod 5 determines A0, and Z mod 5 squared determines A0 and A1, and Z mod 5 cubed determines A0 and A1 and A2, and that inverse limit is exactly what gives us this. And that is what we use. That's how we solve diaphantus's equation. Okay, so it's an inverse limit. So this is another aside. And let's ask, is ZP?
What do you do once you have all these maps?
Then the inverse limit is the unit thing that has to be that.
So an element here, an element in ZP is a list of elements in each of these is really a list of elements. I guess I can call them A1. Well, I can call them A0 plus A1P, A0 plus A1P plus A2P squared, and so on. It's really an infinite list
Oh, and they
where
have to be-
A0 is in Z mod P, A0 plus A1P is in Z mod P squared. This is in Z mod P cubed, such that
they're all compatible.
they're all compatible with the reduction maps.
I see.
Okay, so that's the way that you identify X with this sequence. That's exactly what inverse limits are. We won't need that. The compactness we will need, because we're gonna, measure theory, you need to know what things are compact and what isn't compact. Is ZP compact? This is a question for people who don't already know. We saw that QP was not compact. So we have some arbitrary open cover. How in the world are we going to find some kind of finite subcover? Good, good. It's not obvious. QP is metrically complete. Yes, it's the metric completion of. You have, okay, so the things that you're used to from Euclidean space, not all of them. So for example, closed and bounded is not equivalent to compact, but in metric space, something is equivalent to compact. Sequential compactness. Negative terms? With negative, yes. Okay, so let's talk about sequential compactness. So in a metric space, compactness is equivalent to sequential compactness. Sequential compactness, i.e., every sequence, every infinite sequence in Zn, in Zp, has a convergent subsequence. Convergent subsequence. So this is going to be much easier to think about, perhaps, than compactness. Actually, it's closely related to this inverse limit. So if I have this infinite sequence, I can look at the first digits. There's only finitely many first digits. So some first digit occurs infinitely often. Some A0 occurs infinitely often. Infinitely often. So fix that A0. And let's call this sequence X. Let X1, let's X0, subset of X, be the set of X in Xn in X, such that A0 of Xn is this A0, is this fixed A0. Then I keep iterating. This is an infinite sequence. I only have finitely many options for A1. One of those is infinite. So I get this chain X0, X1, X2, and so on, where these all have same A0 and A1. These all have the same A0 and A1 and A2. And now I just take let X, let me make a new sequence, yn, which is the nth term in the nth sequence. So it's this Cantor diagonalization argument. And these converge in ZP. Because I've specified the first digit, I've specified the second digit, bless you, I specified the third digit, and these are all compatible. And it's exactly what's happening when you take the inverse limit. Okay, so the answer is yes. And a sequential compactness argument will give that. Okay. Is QP, so it's not compact, but ZP is compact. Is QP locally compact? Is QP locally compact? So locally compact means anybody who doesn't already know. Anyone who doesn't already know what the definition of local compactness is can tell me the definition of local compactness. Well, what should it be? I.e., for every point in QP, there exists an open set around this point X, and there exists a compact that contains your open set. Okay, so that's local compactness. Bless you. You don't just want to say there's a compact set because take that singleton. So you want to say there's an open set which is contained inside a compact set, and I always find such a thing. So is it locally compact?
So, I've never heard that before, but I just ask, this is like, you have a closed and bounded set, nine, it's closure.
If you have a closed and bounded set in Rn, then it's
Or like
already
if you take
closed.
No, if you, then you close it, and then that's a compact set, so does that mean that Rn?
Sorry, in Rn, closed and bounded is equivalent to, what am I missing? If it's,
No, if you take an open set and then you close
Ah.
it, so is Rn is locally compact?
Rn is locally
I was
compact.
just asking to make sure I.
Yes. Rn is locally compact. I take a ball, I take a point, I take an open ball around that point. And then I take a square that contains that point. Yeah. So how about here? So I give you some points. So we're given X is, what do I keep writing? 3, 7 to the negative third plus 2, 7 to the negative second plus 4, 7 to the negative 1 plus 5 times 7 to the 0 and so on. How are you going to find an open set around this that is compact? That is contained in a compact set. But actually what I said was okay too. For example, yeah, I mean, to find an open set containing X, what's an open set? We can look at cylinder sets. I just choose some random place and free up these variables, free these coefficients. That's an open set that contains X. So this is my U. Free these coefficients gives me a U. Now I want to find a compact set that contains that. But what is this U? This U is this part of U is ZP times a seventh. So there's a seventh times ZP, Z7, plus a shift. 3 times 7 to the minus 3 plus 2 times 7 to the minus 2.
Like adding a ZP, because we know that's.
I'm just taking compact ZP, scaling it and shifting it by something. This is still compact.
You're really just saying something about how these balls are like one thing to each other.
Yes, and the fact that open balls are also closed balls
Right.
and compact. Yes.
Either, what do they call them, Cloven sets?
These are clopens, that's right. Okay, so yes, it is locally compact. Again, all of these things are trivialities. I for the people who know this stuff, certainly they're trivialities, but they're actually, if you just think about this, the way I see this written in books hides how simple it is. It's just, you just have to have these Taylor series. You just have these power series in P. Yes. Did we do that last time or not? Did we discuss that this is actually how do you multiply to actually, okay, good. Yeah, this is a very good thing because the next thing I think I should talk about is the unit group of ZP. So that'll bring us right to that. So what is ZP cross, the group of units. So by definition, it's the set of elements of ZP for which a unit means you're invertible. There exists another element of ZP such that x times y is 1. 1 is 1 plus 0p plus 0p squared plus 0p cubed and so on. So you're saying this is ZP except for 0. That's a good guess. Okay. So let me give you an x which is not 0. So 0 times p to the 0. Let's do this in whatever 3 or something. I like my primes to be. Yeah, you see something wrong? The inverse, that's right. So I'm about to write something that will have an inverse that's not in. So what's wrong? How come this number doesn't have an inverse in? This, you're saying this is not in ZP. It is in ZP, but it's not in ZP cross. It's in ZP because I didn't start with any 3 to the minus signs. I don't want Joy yelling at me. So this is in ZP, but it's not in ZP cross.
We actually don't know how we're multiplying these things. We're multiplying like a pair series or multiplying the component wise.
So multiplication, yeah, okay. I guess we should have discussed this. It's just like, but with carrying.
Yeah.
But with carrying. Should we do an example? Why not? Is that clock actually accurate? Oh, for once it is. I don't need my phone. Yeah, okay. Let me give you a number that will be invertible. And let's see, let's take a minute and figure out its inverse. So if I put here a 2 instead of a 0, I claim it is invertible. 1 plus 2 times 3 squared plus 1 times 3 cubed. I've given you some information about this number. Parenthesis there. Find x inverse. Let's call this y. So y is going to have some expansion, right? A0, 3 to the 0, plus a1, 3 to the 1, plus a2, 3 squared, and so on. How could we do this?
Oh, that's multiplication 1, 2.
First, yeah, first let's look mod 3. Okay, so x times y mod 3. Mod 3 means all of this is gone and all of that is gone. So x times y mod 3 is 2 times 3 to the 0 plus a0 times 3 to the 0. And if that's supposed to be 1, what did I say? I'm multiplying as opposed to adding. Thank you. So if I look mod 3, it's just this, and I'm multiplying by the mod 3 of that. 3 to 0 is 1, of course. And I wanted that to be 1 mod 3. So that's just twice a0. So a0 had better be 2. Okay, so now I know that this number is 2. Now I look mod 9. X times y mod 9, which is still supposed to be 1. In other words, the next digit has to be 0. The 3 digit has to be 0. Okay, so x mod 9 is 2. I'll stop writing 3 to the 0, and 1 times 3 to the 1. That's x, and y is 2 plus 3a1. I don't know what a1 is yet, and I need that to be 1 mod 9. So this is 5. 5 times 2 is 10, which is 1 mod 9. That's good. And this is 5 times 3 is 15. Mod 9 is 6. 6a1 is 1 mod 9. So a1 had better be, if I subtract 1 from both sides, now I have 6a1 is 0 mod 9. If I divide by 3, I get 2a1 is 0 mod 3. A1 had better be 0. Everybody see that? So A1 is 0. And I continue like this term by term, which, by the way, except for this mod stuff, it's the same exact algorithm as multiplication. You know, when you do 147 times 295, it's the same exact thing as your standard times adding. If you write it out and try to think about what you're doing, that's exactly what's happening. What's really happening is that things that are bigger than 9 get carried later, and I'll have to deal with them later in the calculation. So it is the standard multiplication algorithm. Just now, here we're really seeing the inverse limit play out.
6a1 equals 0, not -1.
So I have x times y is 1 mod 9, and 1 plus 6a1 is 1 mod 9. So if I subtract 1 from both sides, I have 6a1 has to be 0 mod 9. Should we do one more digit? Philip.
And this is these series bounded in one. They're stopped in one direction, so we have a. It's nice like this. It's not like they're going off in two different directions.
Yes, this multiplication would work just as well if you were trying to invert something with stuff to the left, but you would need other stuff to the left, or there'd be a bunch of zeros to be able to multiply, to be able to invert that number. Does that make sense? So what numbers are invertible? So it looks like we're successfully inverting this number x, as opposed to this number, which. Sorry, say it again. Exactly. So ZP, this ZP is the set of all A0 p to the 0 plus A1 p to the 1 and so on, where this guy is a unit. If that first digit is invertible,
There was power series kind of stuff.
yeah, if this first guy is a unit, mod p, then the whole expansion is invertible. And if you think about why that is, right here in this first step, if we can invert this first step, then we can invert the rest. Hensel again. Okay. Question? Good. Yes, please.
So when we do base 10 expansions, not every number has a simple base 10 expansion. You need a plus minus.
That's right.
So like but in QP, we don't have that plus minus.
We don't need a plus minus. Yes. What is -1 in Q3? That's a good question. What is -1 in Q3? Before I do that, should I do one more step here so you can see what the next digit of y would be?
Wait, how do you know the second iteration? Like finding the third digit you need is gonna have a solution.
Let's do it. Let's do it, and you'll see why it has to have a solution. Let's do one more iteration. So now I have 1 is equal to x times y mod 27. X is 2 plus 3 plus 2 plus 3 plus 2 times 9 plus 2 times 9. I'm looking mod 27. Y is, where's my y? Y is 2 plus 0, 2 plus 0 plus an unknown A2 times 9. Right? And now I'm trying to solve for A2. So when I multiply this out, here I have 18 plus 5. 18 plus 5 is 23. So let's call that -4 mod 27. I hope someone's checking what I'm doing. And I'm multiplying that by 2 plus 9A2. So 2 times 4, this is -8, plus 3 times 9 is 0. So this is -1 times 9. So that's -9, -9A2.
As long as your coefficients are in the field, then
Well, now we're at mod 27. Mod 27 is not a field, but this, so let's turn this into positive coefficients so we can stare at them. -8 is 19. Yes, 19. 19. -9 is 18 plus.
that's in the power series, like the coefficients are in Z3.
Yeah, but the coefficient.
Sorry, these are the coefficients. The coefficients in the Z3 expansion. This is in Z3.
I just mean, like, if you're saying, how do you prove that when you multiply these, like, it will always work, I mean, it's like.
This is pretty general.
Yes, this is completely general. The point is, look, there's a 1 here and a 19 here. So I'm going to subtract. This has to be 1 mod, this thing, whatever it is, has to be 1 mod 3, because that's how we found A0 and A1. And it has to be 1 mod 9. So the only thing that I'm worried about, I should be able to divide both sides of this by 9 in a second. And indeed, when I subtract 1 from both sides, I get that 0. This implies that 0 is 18 plus 18 A2 mod 27. Now I divide everything by 9. So 0 is 9, 2 plus 2 A2 mod 3. And so I want to take this to be 2. 2 times 2 is 4 plus 2 is 0. So A2, which implies A2 is 2. And you continue. Joe, you wanted to say something?
No, I think it's like a little bit trickier than seeing it for power series because of the count. Like when you do this, when you do the analogous thing for power series, there's no carrying operator.
That's right.
So it goes a lot smoother.
Yeah, it's much more like this. It's much more like the actual multiplication algorithm where there is carrying, and that carrying rears its ugly head or whatever when you start multiplying these things out, and you'll see that will carry to the next power, to the next power, and so on. But at every point, you have an equation that you know can be solved mod 9. Now you have a linear equation that you're going to divide by 9, and now you just have to solve something like this.
Well, we could work modular 3 to input, right? We didn't have to go for this modular and such, and we could just use how the coefficients are multiplied.
Yes, in fact, another way to do it is just to if I take this number and I multiply it by this number, here it is. Here's why. If I just multiply this number formally, I see what A0 has to be, and then I see that there's a 4 over here. That 4 I'll break up as 1 and 3, and that 3 gets carried into the next place. So yeah, there's a variety of ways. We don't drill children on p-adic multiplication, but if we did, it would be exactly that. We would all be just as used to this as we are to usual arithmetic. I saw another hand, Philip? No? Okay, of course.
I mean, I think there's some last permission was to like the A2 disappeared, like this example, like A2 disappeared and put 2 on the line. And actually, there's in front of the line, and I'm going to take that.
Let me see if I follow you. The A2, yes.
So this line here, 2 plus 3 plus becomes 9.
Here.
Yeah. So the only thing that we're really figuring out is this A2.
Yes,
And we're solving what's going to be in front of the 9.
yes,
And that gets paired with the 2 on the line, like the 2 on the.
that too.
Yeah.
Yep, because everything else is going to be, yeah, so let's just, great, thanks, Forrest, thanks. Now, this A2 is the only thing we're interested in, and it's going to get hit by a 9, which already makes it 0 mod 27. It's going to get hit by a 3, which already makes it get 0 mod 27. So the only thing this is hitting is the 2.
That's how we got to the last.
That's how we got to the last step, and nothing else here is playing any role. So that last digit always has to get paired with the first digit, and the first digit was non-zero. So there's going to be a solution. Thanks, Forrest.
And since just one little comment, and since the first thing was a unit.
Yes,
We were able to get to this last step, because you were able to divide
yes,
right here.
exactly.
Only the-
This 2 is invertible. Yep, it's always that 2 that gets hit. It's always that 2 that hits the next new digit that you're trying to learn about. All the other digits they're gonna interfere with one another in complicated ways. I don't know what the solution is going to be, but it's always going to be 2 times A2, 2 times A3 mod 3, 2 times A17 mod 3 that we need to solve. This thing will be dependent on what happened prior. Great, thanks, Forrest. Okay, measures. 3 minutes. All right. -1 mod 3. Good. We can do -1 mod 3. Yes. Okay, let's do it. What is -1 in Z3? What do I mean by -1? I mean a solution to this equation. This polynomial hopefully is solvable in Z3. That's right. But if we can't solve linear polynomials with integer coefficients, then we have no business doing anything with the p-adics. What do we do? Q is contained in it, yes, but the way that, so we have to give it some expansion to this thing, right? First of all, is this number going to be a unit? Oh, did we finish saying what the units were? I guess we did. Yes, but we didn't finish. There's one more thing that we could say, is just the unit group is the set of all X in ZP. ZP is characterized by the ball of radius, closed ball of radius 1 or open ball of radius 1 plus epsilon. ZP is the sphere. So X in ZP, whose norm is not less than 1 p-adic, the norm goes first, then the p, but is equal to 1, which is exactly the same thing as saying the first non-zero coefficient is the p to the 0 coefficient. Right, so this is the sphere.
Why do you say sphere?
As opposed to a ball. A ball is the inside, the sphere is the boundary. So I want the boundary of, so ZP cross is the boundary of ZP. Okay, that's the invertible. Why? Because if we apply norms, okay, if we apply norms, there's a little. Yeah, if I know that X times Y is 1 and I apply p-adic norms to both, and X and Y both have, and this by multiplicativity is the norm of X times the norm of Y, and both of these are less than or equal to 1, the only way two numbers less than or equal to 1 multiplied to 1 is if they're both equal to 1, which implies X P is equal to 1. Okay, so this is exactly the things of norm 1. And now, why do I know that -1 is in ZP? Please.
Is it actually the boundary in the norm topology?
No. I mean, okay, if you want to say, yeah, anyway. If you want to say you take the disk of radius 1 plus epsilon, or the closed disk, and subtract off the interior, then yes, in that sense, yes. Okay, in our 1 minute, in our 0 minutes left, what are we going to do here? Well, what's the first digit? So X has to have a first digit equal to 2. And then what's the, so now I have 2 plus 3 equals 0. That's good, but I actually want it to be 0 mod 9. Should I write this out? 2 plus A1 times 3 plus 1. So this is the bit of X that we're trying to learn about. Has to be 0 mod 9. So this is 3 plus, so A2 has to be, A1 has to be 2 times 3 times 3 plus 2 times 3 squared plus 2 times 3 cubed and so on. And if you take this number, you just notice that X, this number is 3 times X. So 2 plus 3X, X is 2 plus 3X, which implies X is -1.
I like adding 1 to it and watching the carrying happen.
Yes. Yes, that's a great way of putting it. That's a yeah. Add 1, that's a 3 that carries, that's a 3 that carries, and the whole thing just falls apart. You can look at -1 as 1 over 1 minus 2. And 2 is use the fact that 1 plus lambda squared and so on is 1 over 1 minus lambda. So when I put lambda equals 2, it almost works. I was with you. Until it stopped working. If I don't use the first one, then there's a lambda. There we go. So now I set lambda equal to 2. Oh, that doesn't work.
Better beats. Multiplied by any step is 3, so that is better beat 3.
Yeah, okay, there's something silly. Oh, lambda, yeah, of course, lambda is 3. Never mind.
Yeah. You can do it that way.
Anyway, we solved that one. We will pick up next time with more fun with.
Yeah, you're right.
Oh, in fact, sorry, there is a way to do this. That if you factor out the 2 times 1 plus 3 plus 3 squared and so on. And this is 1 over 1 minus 3, which is negative. Okay, so that's negative. Good. We pick up next time.